So in this class, I will explain about the difference between uniform and non-uniform torsion, that too particularly with regard to non-circular sections, or we can take thin wall sections or I sections like that, channel sections like that. So in the case of uniform torsion in non-circular section, let us consider an I section something like this. It is free at both the ends. So that means it is not fixed, it is not restrained along the length. So this is the length. Length is represented by the z-axis. So it is subjected to torque at both the ends. T is the torque. So ends are free to work. Only Saint Venant's torsion is considered in this case. So you have studied in the case of strength of material, the torsion theory, plane sections remain plane even after twisting. That concept holds good here. So only Saint Venant's torsion, that torsion, pure torsion is called as the Saint Venant's torsion, TSV, that exists in this case. And another thing is the applied torque T, it is resisted by only shear stresses and there are no warping stresses. Out of plane deformation is called as warping. So there will not be any warping stresses in the case of both the ends free. It is the torque is resisted by only shear stress. And in this case, the amount of total angle of twist phi is given by T into Z divided by G into J, where T is the twist applied, Z is the length of the section or length of the shaft we can take, and G is the rigidity modulus of the material, that is of steel we can say, and J is called as the torsion constant. It is called as torsion constant. So this is the expression which is used to calculate the angle of twist in such a case. And the maximum shear stress, tau maximum, is given by Gt into phi dash, where phi dash is d phi by dz, and t is the thickness of the element under consideration. So this is about the uniform torsion, which is subjected to a constant torque. In the case of uniform torsion, the torque is resisted by only shear stress and there will not be any warping stresses. So this is the example of an I section which is subjected to uniform torsion. The shear stress distribution will be something like this. So this is the flange. So this is the shear force distribution in flange, and this is the shear force distribution in the web. So I have shown it separately here. Tau F is the shear stress in the flange, and tau W is the shear stress in the web. So this is the direction. We can call it as shear flow. We can call it as shear flow. And this G into J, this product of G and J is called as the torsional rigidity. Normally it is expressed in Newton millimeter square. So this you have learned in your strength of materials concept, torsion concept also. So this is about uniform torsion. So the thing is, in the case of uniform torsion, only shear stress will resist the applied torque. There will not be any development of warping stresses because the plane sections remain plane even after twisting also. That is their main assumption. Coming to non-uniform torsion, suppose it is the same I section which is having some length z, it is fixed at one end and free at the other end. See, observe here, fixed at one end and free at the other end. If it is fixed, what happens? The warping is constrained or prevented or restrained. That is the difference here. Here warping you will be there at both the ends, but here it is constrained or it is prevented here. So in such a case, please observe that there will be three things here. You have to remember. In such a case, in non-uniform torsion, when one end is fixed and another end is free, and when it is subjected to a torque like this at the end, so definitely there will another reaction torque will develop here in the opposite direction. You can see here, and in this case there will be three effects. One is the bending deformation of the flanges in their plane. So bending effect also will be there for the flanges, and twisting effect also will be there. In addition to that, shear force in each flange will develop. So this is the example for a non-uniform torsion. Here also I have considered an I section like this. So Vf is the shear force that is going to develop in the flanges. You can see that if Vf in this flange is in this direction, the Vf will be in the opposite direction here. I have shown here. And they are separated by a distance h, let us say. So these two shear force components which are separated by a distance h will constitute a couple. So that couple is denoted by Vf into h. That is the thing whatever Tw. The Tw is called as the warping torsion. So this is very important here. So warping torsion takes place in the case of non-uniform torsion, and here you can see this. There will be some lateral displacement here of this center line of the web, or this flange, the center point is displaced here. So that lateral displacement I can call it as u, and this angle that is phi. So if you observe that geometrical relationship, so this is h by 2, this is u and this is phi. So tan phi can be equated to phi because phi is very small. And according to this, tan phi will be u divided by h by 2, or 2u by h, or u is, you can say u is equal to h into phi divided by 2. So this is the relationship between lateral displacement and the strain components. Now in such a case, the total non-uniform torsion will be consisting of two components. One is the Saint Venant's component TSV, and another one is the warping torsion. If the sum of these two is your total non-uniform torsion Tn. So here, how to calculate this Tw? So the Tw warping torsion is nothing but the couple whatever is going to develop due to these two shear forces, which is Vf into h. And we know that if Mf is the bending moment in each flange and Vf is the shear force in each flange, you know the relationship between bending moment and shear force. Shear force Vf is given by minus dmf by dz, where z represents the length of that particular section. So here mf, according to your Bernoulli's equation, you have studied Bernoulli's equation in bending, in strength of materials, the bending moment and this lateral displacement relationship is like this. Mf is equal to EIF into d square u by dz square. You know that the same thing it is expressed in Bernoulli's equation as m is equal to EI into d square y by dx square if it is bending. So in this case we are taking the equation, so where IF is the moment of inertia of the flange about the stronger axis. Normally the vertical axis will be stronger here, so about the stronger axis. Now you know that u is equal to h into phi divided by 2. So if you substitute that in this formula, the equation, Mf is equal to E into IF into d square by dz square of u is h phi by 2. And if you simplify this, E into IF into h is constant here, divided by 2 is constant, into d square phi by dz square. The d square phi by dz square can be written as phi double dash. So you will get an equation like this. Now if you want this Tw is Vf into h, where Vf is once again minus dmf by dz. So I can write it as minus dmf by dz into h. So what you can do here is, here only the phi term is the variable, all others are constants. If you remove that h also outside, you can write this expression as minus E into IF into h is h square divided by 2 into phi triple dash. So where this phi triple dash is nothing but dq phi by dz cube, because that angle phi varies with respect to z. Now warping constant, this term, so this IF into h square by 2, this term is called as the warping constant, denoted by IW. In some books they use this letter also for warping constant. Anyway, in the code we are using IS 800 code, we are using IW as the warping constant. So this is the expression for warping constant for the case of an I section. In the case of an I section, IW is equal to IF into H square by 2. And this, therefore finally what we can write, TW is equal to minus E into IW. This is IW. IF into H square by 2 is IW into phi triple dash. So this is the expression for the warping torsion. So if they ask you to derive the expression for warping torsion, you have to do up to this. And IW for an I section, it is given by IF into H square by 2. And the value of J, so this J is called as the torsion constant. For an I section, the torsion constant is not taken as 1 by 3 into summation BI into TI cube. So this is what I have written here is for I section, or you can take for thin walled sections. So I section is also taken as a thin walled section. So when the thickness is very small compared to the width, so then this formula can be used for finding the torsion constant. Here B is the width of that particular rectangular portion, whether it may be flange or web. Ti is the thickness of that same flange or web portion of the rectangular portion. Now this product of E and IW, it is called as the warping rigidity. So this you can see here, G into J is called the torsional rigidity, whereas E into IW, it is called as warping rigidity. Please note that here E is expressed in Newton per mm square and IW is expressed in millimeter power 6. So therefore the unit of this will be Newton millimeter power 4. Millimeter power 4. That is the unit of E into IW. So in the case of non-uniform torsion, torque is restricted by combination of St. Venant shearing stress as well as the warping stress. So this is the difference between uniform and non-uniform torsion for non-circular section or for thin walled sections. Here in the case of uniform torsion, so torque is restricted by only shear stress, there will not be any warping stress, whereas in the case of non-uniform torsion is a combination of St. Venant torsion and the warping torsion. So the torque is resisted by both St. Venant's stress, shearing stress as well as the warping stresses.